Today, modern digital platforms house millions of videos, products, and articles, accessed by billions of active users simultaneously. Operating at this volume without an algorithmic curator creates immediate friction. Content remains undiscovered, users spend their time searching instead of consuming, and engagement drops. The engineering mandate for these platforms is specific. Predict the exact probability that a single user will interact with a specific item, and execute that calculation across the entire dataset. This diagram illustrates the operational constraint. The system has to retrieve and rank these predictions in under 200 milliseconds to prevent page latency. To understand how this calculation happens, we will build the architecture of a modern recommendation system from first principles. We will trace the path of data, starting with the capture of passive user signals, converting those signals into high-dimensional mathematical vectors, and routing them through a multi-stage sorting pipeline. These systems are strict, highly optimized mathematical architectures built to map and monetize human intent. The foundation of this architecture is data collection. Before a system can recommend anything, it must translate user behavior into computable signals. Platforms collect two types of feedback. Explicit feedback includes conscious actions like star ratings and written reviews. Implicit feedback includes passive behaviors like watch duration, click-through rates, and scroll speed. Engineers rely almost entirely on implicit feedback. Users rarely leave ratings, but they constantly generate passive data. This provides a continuous, high-volume stream of mathematically reliable interaction signals. These signals are aggregated to construct distinct digital profiles. User profiles track viewing habits and purchase histories, while item profiles categorize genre, price, and release metrics. Early systems attempted to match these profiles using straightforward logic. Content-based filtering recommended items sharing similar tags, while collaborative filtering recommended items based on the overlapping habits of similar users. This chart represents a user item matrix. Engineers mapped incoming data onto a massive two-dimensional grid, plotting users against items to calculate overlapping interests. But as we zoom out, the fatal flaw of this design becomes visible. The matrix is almost entirely empty. An individual user mathematically interacts with only a fraction of a percent of a platform's total catalog. A Netflix subscriber will never watch every movie. An Amazon shopper will never view every product. When you try to compare users on this grid, the overlapping data points are virtually non-existent. The math breaks down because there is simply not enough shared history to draw statistical comparisons. Raw signal mapping fails at modern platform scale due to data sparsity, creating a need for a mathematical method to compress space and uncover patterns. To solve the empty grid problem, engineers use a technique called matrix factorization. Watch how the large, sparse matrix is processed. The algorithm decomposes the grid, compressing it into two smaller, densely packed matrices. Labels appearing here reveal latent factors, hidden characteristics like a preference for comedy or action that the AI learns without explicit programming. Modern systems powered by deep learning evolve this concept further by representing these latent factors as embeddings. Look at this coordinate space. The algorithm converts users and items into vectors, plotting them as distinct points inside a shared high-dimensional environment. The rule is strictly geometric. An item is highly relevant if its vector is in close physical proximity to the user's vector. The system measures the distance between these points using specific geometric formulas. The most common metric used is cosine similarity. Cosine similarity calculates the specific angle between two vectors. A smaller angle yields a higher relevance score, indicating a closer match in underlying characteristics. The AI does not watch the video or read the product description. It only understands the mathematical distance between vectors in an embedding space. Finding the closest vectors works in theory, but running that calculation across billions of items every time a user refreshes their app hits a strict computational wall. It cannot be done in real time. This diagram illustrates the structural solution to that bottleneck, the multi-stage pipeline. When the top section activates, we see the first stage, candidate generation. The system evaluates millions of items and filters them down to a tight cluster of a few hundred candidates. To move this fast, candidate generation relies on broad vector similarity and computationally cheap heuristics. The goal is rapid retrieval of a roughly relevant pool. Those surviving candidates drop into the narrow section of the funnel, entering the ranking stage. Here, the system passes the small cluster through complex neural network nodes. Because the candidate pool is now small, the system can deploy heavy machine learning models, like gradient boosting, to evaluate each specific item and predict its exact interaction probability. At this exact moment, the system injects context awareness. Variables like the user's local time, device type, and even weather are fed into the active ranking nodes to adjust the final score. The final output of this ranking calculation becomes the prioritized list of content presented on the user's screen. The pipeline is an exercise in resource allocation, executing cheap math to quickly filter noise, and applying expensive deep learning to sort final results. Zooming out reveals the complete architecture. The final output feed connects directly back to the initial data collection layer, forming a continuous feedback loop. This loop enables online learning. As a user clicks, watches, or ignores the ranked items, those interactions continuously update the system's vector embeddings in real time. However, a perfectly optimized feedback loop carries a structural risk: popularity bias. If an algorithm optimizes solely for immediate clicks, it creates a self-reinforcing cycle. Highly clicked items get recommended more often, creating stagnant filter bubbles and severely penalizing brand new content that lacks interaction data. To prevent the system from stagnating, engineers tune a fundamental algorithmic trade-off: exploitation versus exploration. Look at this interface. When the gauge shifts to exploitation, the system maximizes short-term engagement by showing safe recommendations calculated from historical data. But moving toward exploration, it deliberately injects novel, risky content, testing new categories to discover shifting user interests. This exploratory mechanism provides the technical solution to the cold start problem, allowing fresh products with zero historical data to accumulate the interaction signals they need to be ranked. Modern recommendation platforms constantly adjust this balance. They sacrifice guaranteed immediate clicks to ensure a dynamic, evolving feed that secures long-term user retention. As these data streams weave together, we see the complete structure operate in unison, scaling past sparse matrices, routing through multi-stage pipelines, and continually refining itself through balanced feedback loops. Building a modern recommendation engine requires constructing a scalable mathematical environment capable of predicting and adapting to human behavior at global scale.